Let's start. It's a great pleasure for me to introduce today on our seminar Andrei Bulatov from Simon Fraser University with talk about complexity of CSP-based ideal membership problems. Please, Andrei.
Okay. Добрый вечер. Hello, everyone, and thank you for having me here. What I'm going to talk about today is a recent project of myself with my PhD student Akbar Rafi. The overall idea of the project is to apply some techniques and results that have been developed for the constraint satisfaction problem to somewhat different area that is related to polynomials, polynomial ideals, and computational problems related to those fields. So since that's the area, I guess, somewhat alien to many people here, I will try to introduce the basics of the two things, or the two areas, like this polynomial stuff and the CSP. Then I will show what is the connection between them and how this can be useful in various areas. And if any time remains, I will probably talk a little bit about our own results. Well, they are fairly initial, so not very conclusive. So maybe it's not so important as an introduction to the field itself. Okay, so let's start with the polynomials, polynomial rings of polynomials and polynomial ideals. Well, I discovered that at least among computer scientists, well, this area is either taken for basically granted as a very basic knowledge, or on the other hand, for some other people, it's just they are totally ignorant about this stuff. So just in case, I will introduce some definitions here. So what we are talking about, we take a field. We can imagine in general, well, today that this field is just real numbers. And we are looking at the ring of polynomials that may depend on many variables, so multivariate polynomials over this field. Coefficients are from that field. So what we are talking about is just regular real polynomials, very well familiar object here. Well, they form a ring, which means that we can add up polynomials, we can multiply polynomials. Okay. An ideal in this ring is just a general abstract definition of ideal. In this case, it's going to be a set of polynomials that is closed under addition. So if I have two polynomials that belong to the ideal, their sum must belong to the ideal. And also it's closed under multiplication by any polynomial. So if I take any polynomial but if I take a polynomial from the ideal multiplied by any polynomial, I should have a polynomial from the ideal again. So the obvious computational problem related to this concept that has been studied for, I don't know, a century maybe by now, membership problem. It's very simple and natural. Suppose we have an ideal, we're given a polynomial. The question is, does this polynomial belong to the ideal or not? So in algebra and in many other areas, it's just a standard membership problem. Check if something belongs to a certain set. Well, a polynomial ideal in this case. Again, the kind of natural question that arises here is how do we represent an ideal, right? A polynomial really is an infinite set. Ideals in general are polynomials. So in order to do any computations, we need some kind of finite representation of this, of those objects. A single polynomial, it's clear how we represent it as just a sum of monomials in a regular way with coefficients. For ideal, we normally represent it by generators, which means that this is the smallest ideal that contain all these polynomials. Well, I will give some examples concerning that. So that's what we should know for now. Fortunately for us, we have this classic result that's called Hilbert's basis theorem that says that any ideal of a polynomial ring has finitely many generators, which means that our ideal membership problem, the IMP, is pretty general. And we can use here any ideal and therefore any polynomial. And well, we always have a finite representation of such ideal. And so we can always compute something. Okay. How can we solve an IMP? So since we have these sets of generators, the more general or the more specific rather formulation of the IMP could be given as follows. So we're given a polynomial. This is our input polynomial f. We are given the generators of our ideal, and what we need to do, we need to verify if our polynomial belongs to the ideal. Well, again, it's a simple algebra to show that actually what it means is f belongs to the ideal generated by f1 of m, if and only if I can represent it as a linear combination of those polynomials, where coefficients are not just numbers, they can also be other polynomials as well, just arbitrary polynomials. So what I want to know more specifically is, given a polynomial and a bunch of polynomials, if I can represent this polynomial as a linear combination. Again, since everybody knows linear algebra, that should be very natural approach indeed. Okay, so we can, well, that would be a decision problem. Can we represent it this way or not? We can also ask the search problem. We'll find those polynomials, and well, in that case, yeah, well, we just need to find them. By the way, it's, well, I will mention later that under certain conditions, this can be done efficiently, surprisingly. But okay, well, that's something for some next slides. Okay, so that is our ideal membership problem. Very abstract, no connection to computer science or CSP yet. Okay. Those polynomials H that appear in such linear combination has a special name. Well, this approach, of course, has been studied a lot. These are called a Nullstellensatz proof that f belongs to our ideal. So if I can represent f as a linear combination of f1 through fn, the coefficients of such linear combinations are called a Nullstellensatz proof. Well, the word Nullstellensatz will be clear a little later. Well, it has very much, well, it's very important and relevant in this context. Okay, so let's look at a couple of examples, how IMP can be solved, what are difficulties, and what the difficulties are in general, and so on. So firstly, if I have just univariate polynomials dependent on one variable, everything is very clear. So again, from my experience, the majority of people, when talking about polynomials, imagine univariate polynomials, and that's exactly the case when everything is so simple and clear. So if we have a univariate ideal, just one polynomial, just one variable, then if the ideal generated by some polynomials is actually generated just by a single one, it's well, the greatest common divisor of this family. So for instance, if I have these two polynomials, x squared minus 1, x squared minus 2x plus 1, well, we can easily see that the greatest common divisor of the two is x minus 1. Well, if you're not sure, well, you can check it in probably like 15 seconds. Then this means that, and by the way, the greatest common divisor, which is important, belongs to the ideal generated by f1, f2. I can represent it as a linear combination of the two, and here is the linear combination, and therefore the ideal generated by f1, f2 is the same as the set of all polynomials divisible by x minus 1. So that would be our conclusion. And clearly, in this case, the IMP makes no sense. It's too easy. Great. But if we have multivariate polynomials that have multiple variables, well, things are a bit complicated. So let's look, for instance, at these two polynomials. Well, they don't have any non-trivial greatest common divisor, right? But we cannot claim that the ideal generated by those polynomials is also generated by their greatest common divisor. We just don't know. It's not quite clear what is going on here, right? Well, for instance, the polynomial x squared plus y is a linear combination of the two, and so it belongs to the ideal. But in some sense, well, it doesn't seem to be very much related to any of them. It's not clear why it should belong to the ideal, and so on and so forth. So when we have multiple variables, things are becoming quite complicated. Okay. So if we go back a little bit, and if we look at all these linear combinations, for instance, one kind of natural idea how we can solve the IMP would be something like this. I take my polynomial and try to divide it by the basis polynomial. Say I try to divide it by x2, I may be getting something. I try to divide it by, I don't know, xy minus x, and maybe I am getting something. And if I am not getting 0 after all this division, well, maybe it doesn't belong to the ideal. Unfortunately, in the general case, it's not quite that simple. And a very simple example shows that it's indeed the case. So for instance, if I have the same two polynomials f1, f2, and I want to know if another one, x squared y plus y, belongs to the ideal generated by f1, f2. If I'm lucky, if I start dividing, and if I'm lucky, I can very easily conclude that yes, it belongs, because it's just y times f1, right? So it does belong to the ideal. But if I do it in the wrong way, and I start, say, dividing first my polynomial by xy minus x, then this is what I get. I divide by xy minus x, the remainder would be x squared plus y, right? Then x squared plus y can be divided by x squared plus 1, of course. And, well, the remainder here would be y minus 1, and so I don't know, I don't really know, right? If I divide by those polynomials in different order, say by f1 first, I get something very conclusive. If I divide by f2 first, well, I am getting something that I don't really like. So generally speaking, just by simple manipulations of polynomials, we cannot solve the IMP. It's not that simple. Fortunately, there is a method of constructing a very special basis with very special properties. It is so-called Gröbner basis. I don't want to go into the details, but the intuition here should be that, well, related to linear algebra, for instance. A basis of a vector space, for instance, can be some bunch of vectors, but a Gröbner basis would be an orthogonal basis. So somehow polynomials in the Gröbner basis are very nice to each other, and they behave very nicely with respect to each other, and so on. Okay, so I don't want to go into details here, but if we have a Gröbner basis, we can just divide our given polynomial by basis polynomials, and eventually we will decide if we get 0 in the end, then the polynomial belongs to the ideal. If we don't get a 0 in the end, the polynomial doesn't belong to the ideal. So one of the standard ways of solving the IMP is construct a Gröbner basis and do all this division stuff with the Gröbner basis. So the difficulty here is that even if we start with a small set of polynomials and try to construct the Gröbner basis of the corresponding ideal, the Gröbner basis can be very large. It's always finite, but it can be exponentially large. So sometimes also there is an algorithm that constructs a Gröbner basis. Well, the algorithm may be very inconclusive in the sense that it may take exponential time to complete. Okay, so that's all for now about the IMP itself. So let's see how all this polynomial stuff is related to complexity algorithms and things like that. Okay. All right, so if I take any combinatorial problems, for instance, let's take two-color. Say I'm curious if this graph is two-colorable. I can easily express it as some bunch of polynomials. I can express the constraints that imply two coloring as a bunch of polynomials. So in this case, I would construct two sets of polynomials, and well, I explain what this set is. So my claim is that I can construct a bunch of polynomials such that my graph has a two coloring if and only if those polynomials have a common zero. And then in a minute, I will show that having a common zero is actually related to polynomial ideals as well. Okay, so what do we have here? The first batch of polynomials like that. Remember, I am looking for zeros of those polynomials. So the first batch of polynomials basically tell me that if I want a zero, then x has to be either 0 or 1 and nothing else. It cannot be anything else. And so does y and so does z. So in some sense, the first batch of polynomials just tells me that I have to take x and y only from the set 0, 1. So those are sometimes called domain polynomial. And I'm restricting the possible set of values for the variables in those polynomials. And finally, the second set basically tells me that the color, the value of every pair x, y, x, z, y, z have to be different. Right? So if x and, for instance, if x and y can only be 0 and 1, the polynomial x plus y minus 1 basically tells me that x and y must be different. So they have to get different color. And so that, in a sense, describes the graph. And so it's called the instance polynomial. Okay. Now, what's the connection between zeros and polynomial ideals? This is another classic result, which is called Nullstellensatz. And it basically says that if I have an ideal, which have some additional property that is not important for us, because for us it's going to be automatic, that if we have a radical ideal, and we take the set of zeros, of all zeros of polynomials from I. So this is the set such that every polynomial from I vanishes at every point from V, right? And these are all points like that. Then Nullstellensatz says that any polynomial that vanishes at every point in V, in that variety V, belongs to the ideal. So in a sense, for ideals of this type, radical ideals, the sets of zeros of polynomials in the ideal is the same as the ideal, determine the ideal. Okay, and in that sense, I can replace the ideal with a variety, which is just a bunch of points. Okay. So, for instance, the graph from the previous slide, which is just a triangle, right, has no two coloring, if and only if the polynomials, that's those 6 polynomials from the previous slide, have no common zero. Right? Remember that this is what we concluded, that a two coloring exists if and only if those polynomials have a common zero. This means that this graph doesn't have a common a two coloring if and only if those polynomials don't have a common zero. And this means that the variety corresponding to that ideal is empty, and therefore every polynomial belongs to that variety. And if you think about it, it is the same as to say that the constant polynomial, say 1, belongs to the ideal. Because a constant polynomial like 1 generates the ideal of all polynomials, right? I can multiply 1 by anything, and so I can get any polynomial at all. And well, in this case, it's indeed possible. I can express 1 as a linear combination of those 6 polynomials. Actually, I need only four of them. So this is one of the domain polynomials, and these are the instance polynomial. Okay, so I can prove that there is no two coloring by checking if a certain polynomial belongs to the ideal. Okay. And again, well, this is a very basic connection, right? It has been studied very, very thoroughly for decades. There is nothing new about it, of course. So generally speaking, well, the IMP and well, this approach provides a tool or a witness in this case, that an instance of our combinatorial problem has no solution. How would we do that? Well, we would encode our problem first through polynomials somehow, right? Then we would check if one constant polynomial belongs to the ideal generated by F1, Fn, or maybe we find a proof that it belongs to the ideal, well, whichever we prefer. And if that is true, we conclude that our problem doesn't have a solution. Doesn't have a solution. By the way, a side note, if we can impose some kind of nice condition on those H1, Hm, for instance, suppose we know that our problem is such that if this is possible, then I1 Hm can always be chosen to be of degree at most 5 or something like this. Then I can actually algorithmically verify if such polynomials exist. What I need to do in this case, I need to write down H1. Remember, if they have bounded degree, I can just write them down completely like all monomials up to a certain degree with unknown coefficients, and convert this equality into a system of linear equations that I can then solve, or at least check if it's consistent or not. So if I have an extra information, an extra condition on H1, Hm, for instance, I know that if this is true, then H1, Hm can be chosen of a low degree. I can actually verify that. So it also gives me an algorithm. Okay, what I described here is the known as Nullstellensatz proof system. And of course, people care a lot about the proof complexity. Well, those restrictions, for instance, on the degree of the proof system, of the proof, and so on and so forth. So that is a big area. A lot of people work there. There are a lot of results that we will not need today that much. Okay. So we can do a little bit more than just checking if there is a solution or not. Such proof systems are also used to approximate things, to solve optimization problems. How could it work, for instance, in our case? So what I want to do, I want to try that it's not that my problem doesn't have a solution. I also wanted to say that my problem doesn't have anything close to a solution, right? I cannot, well, some optimization function, well, it is very far from 0, for instance, or something like that. How it's done usually? How is it normally done? Normally, we would construct some sort of a loss function, right, such that this function is 0 on every solution, and then we would prove some lower bound for this function, right? And this way, we would say, okay, since our loss function is at least say 1, this means that there are no solutions because it's supposed to be 0 on any solution, and also it's fairly far from solutions, right? Well, we cannot get anything close to a solution. Well, there is a gap between 0 and 1, quite significant. Okay? So in our simple example, for instance, we can start with our graph again. These are our polynomials. And what I want to say is that there is no solution of this instance on 0, 1. And I would say, I would represent it somehow like this. I would say, okay, well, let my loss function be this thing, right? The sum of squares. And then if I can prove that this function is always at least 1 on 0 and 1s, or when x, y, z are zeros and 1s, then I'm golden. I've proved that not only there is no solution, but okay, well, I can only get fairly far from solution. So what people have been using quite a bit is exactly this approach, and how we prove that our function is at least 1 is we would subtract 1 from that and represent it as a sum of squares. So with this idea, representing things as a sum of squares, well, what we get is another proof system that can work for optimization problems, that used to be very popular and is still very popular, but it has been very, very popular maybe 7-10 years ago, which is called SoS, sum of squares proof system. So more specifically, how it works. Suppose I have a bunch of polynomials, P1, PL, right? Say well, those polynomials may serve some purpose. For example, in the previous example about the graph and two colorings, those may be domain polynomials that basically say what I want is that x, y, z can only be 0 and 1 and nothing else. So the polynomials would impose some constraints on the interesting points, interesting value of the variables. Then I will say that a polynomial has a sum of square proof of non-negativity from this set of polynomials. If I can find two collections of polynomials G1, Gk and H1, HL, such that f can be represented as a sum of squares of g's, of polynomials g, and also linear combination of the pi's. Well, if you think about it, what does it mean? Remember, I don't care about those values of the variables that do not satisfy my polynomials p. Right? So, for instance, I don't care if what my function is. Well, if x and y are not 0 and 1, right? So, in that sense, I only care about those values for which this part is 0. But if this part is 0, then I am saying f must be at least non-negative, right? Because it's a sum of squares. So, for instance, if my previous example, I can represent f, well, that function f minus 1 in this way, then I would conclude that the problem I have doesn't have a solution, and the minimal value is at least 1. The minimal value for that function is at least 1. Right. So, and this way I can actually approximate the actual optimum of my functions by representing my function this way. Okay. So again, sum of squares proof system has been studied very, very thoroughly. Lots of results, many problems can be solved. And again, it has been very instrumental to getting a great number of great results. So a little bit more about that. So for instance, again, if I can find an SOS proof of low degree, meaning that polynomials g's can be chosen of low degree, say bounded at most 5, degree of most 5, and also the coefficients h1, hl can be chosen of low degree, like at most 5. Then again, I can play the same trick. I can write them down as polynomials with unknown coefficients and reduce everything to a system of linear equations, like with Nullstellensatz proofs. But there is a catch in this case, because I also want to make sure that the polynomials from the SOS part are actually squares of polynomials. Again, if you think about it a little bit, this simply means that those polynomials have to form a positive semi-definite matrix. So the actual problem I'm going to solve here is solve a system of linear equations that satisfies this positive semi-definite condition. And this can be done in polynomial time using, well, for instance, the ellipsoid method or whatever. Right? So in this case, if a low degree SOS proof exists, it can be found. We can verify if it exists. If we know that if it exists, it has to be low degree. Proof systems like this are called automatizable. Say Nullstellensatz proof system is automatizable, and SOS proof system is also automatizable. Right? Well, that's a very good property, because this means that we can use such systems to actually solve problems, not only prove something about properties of problems. Well, there is an interesting accident, I would call, related to this SOS stuff. That actually kind of emphasizes the importance of the IMP part from SOS. The accident is that after some 10 years of studying SOS and claiming that it is also always automatizable, it turns out all of a sudden that low degree is not enough actually to find an SOS proof. What is also needed is small coefficients. Ryan O'Donnell came up with an example that shows that you can have a low degree proof but no proof that satisfies that positive semi-definite condition has a polynomial size coefficient. So coefficients must be huge in this case. Well, which is a little bit of a downer. But nevertheless, well, the situation was almost saved by Professor Gavendra, who showed that in the majority of interesting cases, the only condition that matters, that actually guarantees that coefficients are small enough, would be polynomial time solvability of the IMP problem. So in that sense, we can use SOS if we can use IMP, at least in the majority of interesting cases. There are some kind of weird cases, but we don't care about them at the moment. Okay, so in that sense, the IMP is quite important as well. Okay, that's all for now about polynomials and proof systems. So let's now talk about CSPs. Okay, we don't actually need to know much about the CSP beyond the definition. So what I'm going to do here, I'm going to introduce a definition, give a few examples, just to create a little bit of intuition about this. Then I will introduce symmetries of CSP, so-called polymorphisms. But again, we don't need to know much about polymorphisms, well, nothing beyond the idea that they're kind of useful, and then they're very helpful if we want to express some properties of a CSP. That's all we need, actually. Well, I will use some specific terms and notions here, but well, we don't even need to fully understand them. That's just the overall idea that somehow useful will be enough. Okay. So first of all, constraint satisfaction problem. It's a general framework that includes lots and lots of different combinatorial problems. The framework goes as follows. In my problem, I have a bunch of variables. We're talking about variables again, right? And they have to satisfy some constraints, where every constraint can be thought of in the most general sense as a relation, such that only tuples that belong to that relation are good for us, right? So all the values of those variables have to satisfy certain constraints, meaning that local combinations of values, well, must be some of these special kind, okay? And what we're looking for an assignment to x1, xn that would satisfy all the constraints. Right, so the overall idea that we have some kind of local constraints that are imposed on small sets of variables, but what we want to find a global solution. And well, even from here, it's kind of clear that we can include a lot of problems into that, right? Into this framework. What people do quite often, they say, okay, well, if allowing just any constraints is probably meaningless because, well, they are any. Right, too many. So what people usually do, they normally say that, okay, we are going to use only relations from a certain fixed set, which is called constraint language. And this is going to be our CSP, constraint satisfaction problem. In this case, the notation for CSP would be CSP of gamma. So this simply means that I fix a constraint language, a bunch of relations on a certain set, say A, for instance, and in my constraint satisfaction problems, I'm only allowed to use relations from that set, nothing else. It turns out even these, with all those restrictions, I still can capture a lot of interesting problems. For instance, the satisfiability problem. What is the satisfiability problem? It is, well, we are given a CNF, right, and we want to know if it's satisfiable or not. Well, I don't want to take arbitrary CNF, say I'm talking about 3 CNFs, right? Every clause contains exactly 3 literals. Then what do I have? Then every clause is a local constraint on some variables, right? Well, X, Y, Z may satisfy or not satisfy this specific clause, well, a constraint in our language. And I want to satisfy them all. I have conjunction between clauses. Right, so 3SAT is actually a CSP where constraint language or every relation from a constraint language is given by a 3 clause. So there are 8 different 3 clauses. So gamma 3 sub would contain 8 ternary relations, and well, everything is just perfect. Okay. Graph K coloring, for example. Another example of a CSP. Say, what is a coloring? Well, it's a graph, right? This is our graph. We have to assign one of the K colors to every vertex of the graph in such a way that adjacent vertices get different colors. Again, if you think about it, we assign values to vertices. So vertices are our variables and colors are values. And such an assignment has to satisfy local constraints. Adjacent vertices get different colors. So in a sense, I can think about it as a CSP where for every edge I have a constraint, just telling me that the values of those 2 variables must be different. So graph K coloring is just the CSP of the disequality relation. Right? Okay, graph K coloring is here as well. What else? Well, one of the formulations of the so-called unique games. In some sense, it's a general. Well, it's not generalization, frankly, but anyway. So it's again something similar to K coloring. Also, instead of disequality, I use more restrictive relations. Say instead of again, I have a graph, but now instead of K coloring, disequality relation, I'm using permutations on my set, something like this. The requirement is that the value of xj has to be, well, the function of xi, for instance, right? And the goal is to check if such an assignment exists, or in actual problem that has been studied for so long. The requirement is also if it's not possible to assign values in such a way that all constraints are satisfied. We want to satisfy as many constraints as possible. And the very famous games conjecture basically says that, well, I cannot do that. I cannot approximate this problem in any reasonable way. Again, details are sort of not very important for us here. Okay. Well, invariants and polymorphisms, again, I will give definitions and a couple of examples, but in a sense, well, the main idea for us would be that just these things are useful for CSP, and we can express various things using polymorphisms in this case. Okay, so the formal definition. I say that a relation is invariant under, say, an operation F on the same set. So relation is on a set A, F is on the same set A, or I will say that F is a polymorphism of my relation. If I take any tuples from my relation, apply F, the result also belongs to the relation. Okay, so in some sense, relation is closed under F. Again, I will give a couple of examples, and hopefully this will be a little bit more intuitive. Okay, so well, there are a lot of such operations. Usually, the set of all such operations I will denote by pole of gamma. Well, there is unfortunately some kind of a potential collision here between polymorphisms and polynomials. So these are different things, right? Polynomials are with real numbers, polymorphisms are kind of finite objects. And pole means polymorphisms, not polynomials. Right? So let's try to remember that, and hopefully we will avoid confusions here. Okay, why polynomials are interesting? They are very important for the CSP for the following reason. If I have 2 CSP problems, CSP of delta and CSP of gamma, so delta and gamma are 2 constraint languages, and I know that every polymorphism of delta, or of gamma, sorry, is also a polymorphism of delta, then I know that CSP of delta is easier. So in a sense, polymorphisms rule the complexity of constraint satisfaction. Right? The only thing I need to know in order to figure out what the complexity of CSP of gamma is to know the set of its polymorphisms. This is why it's important, and this is why we are going to use it to some extent. Okay, now a couple of examples of polymorphisms. So first of all, let's take a so-called affine relation. What is an affine relation? Again, imagine you have a field, say finite field in this case, and you have a system of linear equations, some kind of small system of linear equations over that field. Right? Then, well, it may have some solutions, of course, right? So the set of all solutions form a relation, right? As far as we know from linear algebra, this relation is going to be a coset of some subspace or of a subspace of some vector space. So it's all kind of linear algebra, right? So suppose that our relation is given like this. It's defined by a system of linear equations, and this ax equals b is the system. Okay? Suppose we have a relation that is given by a system of linear equations. I claim that it has a very, very nice polymorphisms. So one of those very nice polymorphisms is this operation x minus y plus z, so-called affine function. Plus and minus here are in the sense of the field. Remember that we have a linear system over a field, finite field, and plus and minus here are also in the sense of that field. Okay, so let's check that yes, indeed, this is a polymorphism of that relation. Right? I don't know any specific tuples there, but I know the property, how the relation is given. Okay, so what do I need to do? I need to take any tuples from the relation, so x, y, z from the relation from R. And what does it mean? It means that x, y, z satisfy the system of linear equation. So ax is b, ay is b, az is b. Okay. Now, what do I need to verify? I need to verify that if I apply f of xyz to xyz, then again I get some tuple. I again get some tuple. This tuple must satisfy the system of linear equations as well. Right? So that's what I need to do. How do I do that? Well, in a very simple way. I compute the f of xyz, here it is, and multiply by the matrix and check if I get b in the end or not. Okay, well, it's a linear system, right? It's usual multiplication by a matrix. So, well, it is distributive. I can do it like this. Ax, ay, az equal b, and therefore what I get is also b. So x minus y plus z satisfy the system of linear equations, and therefore x minus y plus z is a polymorphism. So this is what we would do about that. Okay. A slightly more specific example, let's take some very special relation and a couple of very special functions, and again, see how we get that one of them is a polymorphism or not. So again, let's take a simple ternary relation, right? So tuples here are written vertically. So the tuples in this relation are 0, 0, 0, 1, 1, 1, 2, 0, 1, and 2, 2, 2. Right? So 4 tuples. And I take two binary operations. Again, what does it mean? Well, if we think about the symbol as multiplication, it means that 0 times 0 is 0, 0 times 1 is 0, 0 times 2 is 2. 1 times 1 is 1, etc., etc. Okay. So let's see if this operation star is actually a polymorphism of our relation R. Well, I claim it's not, because if I multiply 1, 1, 1, that's a tuple here. By 2, 0, 2, that's another tuple here. I get something. Let's try to multiply. 1 by 2. 1 by 2 is 2. Okay. 2. 1 by 2 is 2. And 1 by 0. 1 by 0 is 1. It's 1. Well, I get another tuple. And this tuple is not in the relation. Therefore, it's not a polymorphism. So this is the way how I can conclude that something is not a polymorphism. Right? Let's take another operation. Again, some sort of multiplication. Well, in this case, I change the values slightly. And it is actually a polymorphism of this relation. But to verify it's a polymorphism, what I actually need to do is to take all pairwise products of the tuples and verify that every time I get a tuple from the relation. For instance, 1, 1, 1 times 2, 0, 2 is 1, 1, 1, belongs to the relation. 0, 0, 0 times 2, 0, 2. It's going to be what? It's going to be 0, 0, 0 in the relation, and so on and so forth. So that's the a little bit of a few examples of relations and polymorphisms. Okay. Now, some polymorphisms are good and sort of useful for us, and somehow they define polynomial time solvable constraint satisfaction. So the good polymorphisms I will be mentioning, again, we don't need really details, is the first one is a semi-lattice operation. So any binary operation that satisfies just equations. X times x is x, it's commutative, xy equals yx, and also associative. Say if you look at what kind of satisfiability problems, say CSPs on a two-element set. Satisfiability problems have these semi-lattice polymorphisms. These are exactly those that are given by so-called Horn-Sat. Well, if you don't know what Horn-Sat is, it doesn't matter. Anyway, it's something well known. Majority operation, it's a ternary operation. It probably has to be G, not H. A ternary operation G that just returns the majority of its values. If two values are equal, then this is what we get. Okay, in terms of elements or two-element CSPs, well, this corresponds to satisfiability. Again, a well-known special case of SAT. And also we may have a multi operation, so-called multi operation that satisfies the conditions like that. And in particular, the affine operation we saw on the previous slides is a multi operation. And very often, multi operation gives us a CSP that is actually can be represented as a system of linear equations. And again, something very nice. So all these well-known operations, and they correspond to well-known combinatorial problems. Okay. So how we use polymorphisms to classify complexity of the CSP? Long time ago, like 43 years ago, Thomas Schaefer proved, well, he didn't use polymorphisms, but it's easy to convert his results and state it with polymorphisms. He classified the complexity of CSP of gamma, where gamma is on a two-element set, so-called Boolean CSP, right? So he basically proved that this problem is polynomial time solvable if and only if one of the four cases happen. First of all, a constant operation like constant 0, constant 1 is a polymorphism of gamma. Disjunction or conjunction is a polymorphism of gamma. A majority operation is a polymorphism of gamma. Or the fine or multi operation is a polymorphism of gamma. Well, in all other cases, the problem isn't P-complete. Okay, so that was the classic result, and well, by now we know a complete classification, not only for Boolean CSPs, for all finite CSPs. Also, it took almost 40 years to do that, but anyway, it's slightly more complicated, but again, some sort of condition and well, this dichotomy, complexity dichotomy, can be given in terms of polymorphism. So yes, indeed, polymorphisms are important, and we are going to use them quite a bit. Okay, so that's been a crash course on CSPs. So now let's look at the connection between the IMP and the CSP. So remember that CSP is a finite thing. It's about finite objects on finite sets. Right? IMP is about real polynomials, where real meaning with coefficients that are real numbers. Okay, so how do we relate them? Well, the idea is basically the same as with our representation of, for instance, two coloring. Only in this case, we can take it much more generally than with just two coloring. Okay, so let us start with an instance of a CSP. So we have a constraint language gamma. Let's assume that its base set is a set of just, say, negative numbers from 0 to r-1, whatever it is. But since we're going to use polynomials, we have to use numbers. That's the thing. We cannot use just any elements, right? They have to be numbers. And if we want to use real polynomials, they have to be real numbers, at least. So, okay, so suppose the base set is just the initial segment of natural numbers from 0 to r minus 1. Suppose we have a bunch of variables, well, of that instance. So what are we going to do? I'm going to relate this instance with a polynomial ideal. How do I do that? In the most straightforward way imaginable. For every constraint, remember what is a constraint? It's a relation imposed on a bunch of variables. So it's r of xi1, xik, for instance, something like this. So for every constraint like this, I introduce a polynomial, a real polynomial, in the same variables, whose zeros are exactly the tuples of r. So I interpolate this finite relation with a real polynomial. Again, well, if you think for a few seconds, obviously it can always be done, right? I can always kind of concoct something that has zeros precisely on a specified finite set. That's not difficult. So I can always do that. I can always relate and encode a constraint in my CSP with a real polynomial. Right? I will call this process interpolation of the constraint. Right? And now the ideal related to that instance P is just the ideal of the arena of real polynomials that is generated by those constraint polynomials, plus domain polynomials. The domain polynomials that actually encode, that actually insist that the values of all the variables must be from that set D. So it's actually just one polynomial, fd, but it has to be applied to every single variable. Again, if you remember the example with two colorings, that's exactly what we do. We introduce domain polynomial that say, okay, every variable must be 0, 1, and then we say if they're 0, 1, they better be different. And that's and that would be the instance and constraint polynomials in our sense here. Okay, good. Now, well, that's not all IMP. It's only half of the IMP. It's just the ideal, right? We need input polynomial. So we also, well, the input polynomial doesn't come from the CSP. There is nothing about input polynomial there, or at least almost nothing. So we are going to take input polynomial of any polynomial of our liking. So the instance of IMP of gamma, in this case, is going to be an instance of CSP of gamma and a polynomial that depends on the same variable. Okay, so the polynomial can be done, okay, can be represented explicitly like a sum of monomials. So the goal is check if that polynomial belongs to the ideal IFP. And so it's somewhat similar to solving the CSP, right? We are checking, well, if something belongs to the ideal, etc., but it's quite different, actually. Also, we may want to find a proof that it belongs to the ideal. Okay, so sometimes we want to restrict the problem a little bit, and we restrict it by actually bounding the degree of the input polynomials. So sometimes it's necessary. Sometimes it's necessary. Sometimes we don't know how to solve the general problem, but we know how to solve this degree bounded problem, bounded degree problem. Okay. And the final transformation, well, to the form of the IMP of gamma, we're going to use it. And as we shall see, it really goes quite a bit closer to a combinatorial problem than it used to be in the very beginning. So what I will observe that IFP is always a radical ideal. Well, this is because the domain polynomials belong to that ideal. And so Nullstellensatz applies. This means that IFP is defined by the set of zeros, right? By a set of zeros. And zeros of those polynomials are actually solutions of the CSP, if you think about it. Right? The zeros of the ideal, the variety corresponding to the ideal, are actually the bunch of solutions of the CSP-P. Nothing else but that. So actually what we're asking is, given a polynomial, is it true that every solution of P is a zero of F? So finally, we can translate this ideal membership problem in terms of, well, is it true that every solution is a zero of a polynomial? Well, one thing is kind of, one implication of representation like this, it's quite obvious. Well, if there is a solution of the CSP which is not a zero, right, we can guess it and check that in polynomial time. If I guess a solution of a CSP, I can check if it's a solution or not, right? I can just verify every constraint on it. And I can also verify if a given assignment is a zero of polynomial or not. Which means that IMP of gamma is always belongs to co-NP, right? So, and that's quite a bit of a upper bound on the complexity of the IMP. The general IMP can only be, it is only decidable. Is only decidable, right? We cannot say that it belongs to NP, co-NP, or anything like that. That's too small, right? But for such a combinatorial version of the IMP, well, it's pretty low in the complexity hierarchy, and it belongs to co-NP. Okay, so even such simple observations will give us something. But in general, what we'd like to know about the IMP? Well, question one is what people have been thinking about mostly, right? Remember that IMP has been always solved through Grobner basis, so people don't know actually how any different way. Well, except for that linear equation stuff, unknown coefficient linear equation stuff, but that doesn't apply. It only applies to bounded degree proofs. So people have always been wanting to find a Grobner basis. So that's the truth to go in this case. So the question is always, for which gamma it's possible to find Grobner basis efficiently? For instance, for which gamma it's small. Okay, the second question, for which gamma there is a small Nullstellensatz proof. And that's a question that is basically resolved, by the way, not too long time ago. And again, the answer is surprisingly is in the language that has been used for CSPs quite a bit. It corresponds to a very nice class of CSPs, so-called CSPs or bounded widths. Well, and that is if and only if there is a small Nullstellensatz proof in this case. And finally, the equation we want to solve. We don't care that much about Grobner basis. Also, we don't know many ways to solve the problem without Grobner basis, but actually, let's look at things more generally. So we want to know for which gamma the problem IMP of gamma or IMPD of gamma can be solved in polynomial time. So basically, we want to get a result similar to that for CSPs. Okay, and the start, the result for Boolean IMPs is strikingly similar to Schaefer's theorem. It's fairly recent, right? In these two papers, Mastrolili with his student Harty, obtained something that looks really like Schaefer's theorem. Let gamma be a constraint language on 0, 1. Then, if gamma has a majority polymorphism, we can solve the IMP. If gamma has a semilattice polymorphism, then we can solve IMPD. Okay, that's a little bit less than that. If gamma has an affine polymorphism, then we can solve IMPD. Actually, it seems like we can improve it to IMP, but okay, well, that needs to be verified. In all other cases, IMP2 is going to be complete. So in a sense, this is Schaefer's theorem for the IMP. And we clearly would like to make it stronger, improve it to a dichotomy theorem for general IMP as well. Okay, so let's try to do something, at least. This is where I switch to our own results, and hopefully, how much time do I have?
At least 30 minutes.
At least? Oh, well, I don't need that much, hopefully. Okay, anyway. So that's been around an hour.
Yeah, you can.
Yeah, that's been around an hour, but I probably need more, another 10 to 15 minutes. Okay, so let's talk a little bit about our results. Basically, what we are trying to do is to follow the CSP playbook. What people have been doing for CSPs in such cases, we'd like to do for IMPs. Well, it has been so successful for CSPs. Why is it not going to be successful here? So let's try. Also, it turns out that things are way more difficult, and even simple things, well, since you sometimes need to work with all these Grosvenor bases and stuff, things tend to be a little bit more complicated. But anyway, we're trying. Okay. So first of all, and that's the first step in the CSP research as well, what we try to do is to say something like this. Suppose I have some constraint language, gamma, right? Now I want to improve it in some sense. Usually this improvement is by adding something useful to it. So I want to improve it in such a way that what I get, well, after this transformation is reducible to the original one. So what I basically want to do is to say that I don't need to look at all possible constraint languages. I only want to look at some kind of nice constraint languages and solve the problem for them, right? And that I don't care about everything else. And in CSP, there are several standard steps like that, and that's what I'm with it. And this is what we are trying to do here as well. So one of the standard steps is adding so-called constant relations to the language. What is a constant relation? A constant relation is a unit relation that contains only one tuple. In terms of CSPs, this is basically allowing ourselves to say, this variable must take this value, full stop. Right? So a very strict constraint, like assigning a specific value to a specific variable. That would be a constant relation. This is how constant relations are used. And clearly, in terms of reductions, it's very, very useful. So the good thing about IMPs is that we can add those constant relations fairly pain-free. Well, we may sort of move to slightly higher, to polynomials of slightly higher degree, but this increase in degree is kind of constant. It's the size of the base set. Okay, so that's somewhat an improvement, and we can do quite a bit. Again, it turns out that this is enough to get some what would be that lower bounds on the complexity of some IMPs at least, just immediately. How do we do that? Remember our arguments when we were talking about two coloring, that our graph doesn't have a two coloring if and only if a constant polynomial 1 belongs to the ideal. So if you think about it, our CSP, our instance of the CSP doesn't have a solution. If it doesn't have a solution, the corresponding ideal doesn't have zeros, and therefore the constant polynomial belongs to that ideal. Right? So in a sense, the IMP will encodes the CSP as well, right? It's a special case for a very specific input polynomial. A constant polynomial belongs to our ideal if and only if CSP instance has no solution, right? This means that if we can solve IMP, we can also solve the CSP. So if the CSP is NP complete, well, we know it's that every CSP is either polynomial time or NP complete. So if it's hard, if it's NP complete, then the corresponding IMP is also hard. It's co-NP complete. Right. So just immediately from observations like this, we can get that complexity lower bound on at least some. So all the gain will be among those CSPs or gammas for which the CSP is solvable in polynomial time. And we know a lot about such things. We know a lot about such things now. Okay. The next step would be what Givens proved. Now what? 20-something years ago, about polymorphisms. And it works as well. Say, if we have constraint languages such that every polymorphism of gamma is a polymorphism of delta as well, that IMP of delta is reducible to IMP of gamma. Again, we pay some price in terms of increase in the degree of polynomials allowed, but overall, it's not a large price. Okay, so we have the same role of polymorphisms as for CSPs. So the complexity of the IMP only depends on the set of polymorphisms of gamma and nothing else. So all tools from the CSP can be used here, fortunately. Okay, well, actually, we can do even a little more than just polymorphisms. I will show one more reduction that can be made formal. I don't want to introduce the bunch of definitions, just to give you some kind of idea how things may work in this case, in this kind of reductions. And this will also give me some kind of useful reduction as well. So I will show a reduction from a constraint language on a 3-element set, which is invariant under certain similarity separation, to a Boolean case, which is well known. Okay. And that's basically the way our reductions tend to work in most cases. Okay, so what do? We take any constraint language. I don't know any specific relations. The only thing I know about it is that every relation is invariant under similarity separation, like this. So what does it mean? This basically represents multiplication, right? The similarity separation, multiplication here. So similarity separation is idempotent, which means that 0 times 0 is 0, 1 times 1 is 1, 2 times 2 is 2. Okay. Now, if I multiply two different things, like for instance, if I multiply 0 and 2, I always get the element which is higher here. So 0 times 2 is 2. 1 times 2 is 2. The only question, what is 0 times 1? And 0 times 1 has to be an upper bound for both of them. So the upper bound for both of them is 2, so 0 times 1 is 2. That's the similarity separation. And this is how it's convenient to represent it. Okay? I will reduce IMP of gamma to IMP of delta, where delta is, again, the constraint language, certain constraint language, whose base set is 0, 1, and it's invariant under similarity operation on 0, 1 given by this, which, if you think about it, is just disjunction, right? 0 times 1 is 1, right? According to the same rule, 0 times 1 is 1, so that's just disjunction. How do we do that? We do it as follows. We represent elements 0, 1, 2 as pairs of elements of 0, 1. So let's G is this representation. I represent 0 as 0, 1, 1 as 1, 0, and 2 as 1, 1. It is a good representation in the following sense. If, for instance, I multiply 0 and 1, 0 times 1, for instance, right? I have to get 2, right? Remember that in this semi-lattice, 0 times 1 equals 2. So if I multiply 0 times 1, I should get 2. Now, let me multiply the codes for those elements. I multiply 0, 1 by 1, 0. Oops, sorry. Component-wise. So I multiply 0 times 1, it's 1. 1 times 0, it's 1. So multiplication of elements 0, 1, 2 is the same as multiplication of their codes. That's the important property. That's the important property. This means that if I translate all these relations from gamma using this trick to relations of over 0, 1, every polymorphism here will kind of translate into a polymorphism of delta. Well, in particular, this multiplication. Right. So this property actually allows me to keep the good polymorphism. Okay. So now we know how to transform an instance from CSP. And we know how to transform an instance of CSP of gamma to an instance, say, P star of CSP of delta. And it works as follows. Every variable of P I replace with a pair of x1, x2. Right? Remember, I represent every value 0, 1, 2 with a pair of values. So I need to replace a variable with a pair of values. Okay? In every constraint, I replace a value with a pair of values. Right? Say value A for x with G of A, which is a pair of bits for x1, x2. And for every variable, I add a constraint that says that x1, x2 must be one of the 3 combinations. Right? I don't want anything outside of that. So it's 0, 1, 1, 1, 1, 0. then what I can claim is that, again, it can be verified, that it's very simple to verify, but I'm not going to do it here, of course, that the solutions of P are in one-to-one correspondence with solutions of P star. So I can swap from solutions of P over 0, 1, 2 to solutions of P star, like by substituting those pairs over 0, 1, the codes basically, right, and back. So that's a encoding and decoding, like in a very straightforward way. Now the only thing that remains is what do I do with the input polynomial? Right. So remember that CSP is just an instance, while IMP is a CSP instance that I've done something with it already, but it's also an input polynomial. So what do I do with the input polynomial? Let's consider the decoding function from pairs to 0, 1, 2. Now, clearly, any such function can be interpolated by a polynomial. So, for instance, in this case, g2 minus 1 of x1, x2 can be taken just x1 plus x1, x2. So what does it mean? If I plug in 0, 1 for x1, x2 here, right, what do I get? It's 0 plus 0 times 1. It's 0. Right, so it basically computes the function. 1, 0. 1 plus 1 times 0 is 1. Okay, 1, 1. It's 1 plus 1, it's 2. And so yes, indeed, the values of this little polynomial on the pairs is exactly the values of g2 minus 1, exactly the decoding function. So now what do I do? I'm given that input polynomial, right, f, at an instance p of CSP of gamma. Now I convert p into p star. I convert f into something else. And I convert it simply by substituting this little polynomial g2 minus 1 instead of every variable of f. Okay, so that's just the only thing I do. Instead of every variable of f. Okay. And then I can show that f belongs to the ideal I of p if and only if the resultant polynomial belongs to the ideal of p star. And again, it's pretty straightforward, because I have this nice encoding that is one-to-one, etc., etc. And well, this way we have a reduction from a larger similarities to a smaller similarities. Now, from the result of Master-Lilly, we know how to solve things for Boolean similarities, and we are golden. Everything works. Okay, so the other type of results we proved is a one of the interesting problems still here that remains with all this nice transformation is what if we don't only want to know if something belongs to the ideal, but we also want to find the proof of that. What do we do with the proof? So, unfortunately, well, I have a bad news. I don't know what to do with proofs. I don't know any relationship between proofs in the two cases. Why is that? Suppose we can find a proof for f star. Well, we actually can, because we have this Master-Lilly's result that uses Grobner basis. It allows us to find a proof, etc. Right? So suppose the proof looks like that. Now I want to convert it into somehow a proof for f. Right? How can I do that? I don't really know. Right? Those polynomials are somewhat scattered around. Well, I have some strange variables that are not in f, and so on and so forth. So I don't really know how to do that properly. It might be possible, but I don't really know. Okay, so the second type of results we obtained are just some kind of tractability results that list some IMPs that are solvable in polynomial time, and they are generalizations of the result of Master-Lilly and Harati. So we know that if we take any similarity separation, IMP D is polytime for every D, generalization of this disjunction-conjunction result of Master-Lilly. If I take a CSP which has so-called dual discriminator, doesn't matter what it is, its IMP of that is polynomial time. Dual discriminator is a generalization of the majority function. and I can solve IMP sub D of ZP, not only two-element field, but P prime field, any prime field, prime characteristic field can be solved in polynomial time as well. Well, and we suspect that we actually can do it a little better and show that for any abelian group we can solve it. Well, not ZK actually. For any abelian group, this can be also solved in polynomial time. If I have a fine operation of any abelian group, then the IMP can be solved in polynomial. Okay, that's basically it. A few open questions, which are, of course, well, how about more polynomial time problems? As I mentioned, things are a little bit complicated in this case because we very often need to work with those Grobner bases, and it's technically quite difficult, right? So that's not quite clear how things will develop in this way. It will be very interesting. We have so many techniques for the vanilla CSP, like, for instance, local consistency techniques and so on and so forth. To what extent are they important? To what extent are they important here? How we can use them and so on and so forth. So in some cases, we see some connections, but not always. Well, we need to do something with the proofs. Can we recover proofs, actually? That would be very useful. And this is what many people are interested in actually recovering proofs rather than anything. And finally, very often, well, in those results, we bound the degree of the input polynomial. What it translates into is that we can also bound the degree of polynomials we want to include in the Grobner basis. Right? And what does it mean? This means that we start with a CSP instance, we construct an ideal, right? The ideal well, the Grobner basis of that ideal can be huge exponential time. But then we say, we aren't actually interested in the whole ideal. We're only interested in the ideal that is generated by polynomials of small degree, of low degree. And then we have kind of nice low degree Grobner basis for that. Okay? So the question is, well, what happens if I translate this restriction back to CSP? Do we learn anything interesting about the CSP in this case? It seems that sometimes, yes, in particular for that Horn-Sat, for instance, case, apparently it kind of makes sense to ask about the CSP side as well, but in general, it's quite unclear. So this is all for me. Thank you for your attention.
Thank you very much. Very nice talk. Thanks. Any questions? Are there any questions?
Thank you for the talk. Could you please repeat the part when where it is explained why IMP is in CoNP?
In CoNP, okay. Let's go back. Oh, okay, here. Right. So okay. Should I explain that the constant polynomial belongs to the ideal if and only if P has no solution?
No, it's clear.
That part is clear. Okay. Now we can. Okay. So what is CoNP? It's a class of problems for which there is a polynomial weakness of the null instances. Right. So if the answer to your problem, to your decision problem, is no, I can give a witness that this is the case. Right. NP is the class of problems where I have witnesses, small witnesses for yes instances. CoNP is those where I have witnesses for no instance. Okay, so a witness for no instance in this case would be a solution of my CSP, which is not a zero of the polynomial.
Why would it be small?
Because it's okay. So what is it? What is a zero? Or what is the solution of my CSP? It's a assignment of values to variables, right? I have a polynomial with many variables, obviously, right? It's a part of the input. And solutions are taken from the domain from 0 to r-1. So the only source of kind of non-smallness is that those values are kind of huge, right? Very long. But it cannot happen here because every solution of the CSP well, just gives values from 0 to some number, like natural numbers, pretty small ones, from a fixed range. Does it make sense?
Oh, okay, yes, everything clear. Thank you.
I have a question. Yeah, as you told, so for some problems, by some reasons, you can solve not. So if you want to understand if your polynomial is an ideal or not, you just try to look on solutions with bounded degree. So how can you decide that the degree should be bounded by D?
Well, that's a very good problem actually, right? So we of course don't. Well, if you take just arbitrary ideal or arbitrary CSP or whatever, you don't know that. Well, that's the whole area of proof complexity, right? Well, if I am given this problem, can I actually find a bounded degree in Nullstellensatz proof? If it's a no instance, can I find a Nullstellensatz proof of bounded degree? No. Well, we cannot know it automatically. It has to be proved by maybe some difficult theorems and so on.
So there are some tools that can work for some specific problems.
Yeah. Well, so in some cases, well, it just known that we can do this or that, for instance. Yes. But for the majority of interesting problems, and where you would like to use something like this, well, there is no bounded degree proof. That's highly unusual in some sense.
Thank you. And one more question. So all these results that you mentioned are about so this complexity hierarchy in terms of polynomial time or NP. Can we? Does it work for some, say, graph problems on graphs when you use these reformulations in terms of IMP and it gives something some better than all other algorithms in terms of, say, fine-grained complexity?
Well, overall, if you take any specific problem, like say two-colorability, right, for instance.
For example.
Okay, in this case, if there is a Nullstellensatz proof, well, you can show it. You can find one of bounded degree, for instance, right? So, for instance, well, if you use this Nullstellensatz route to solving things, well, you take your graph, you convert to all these polynomials, you run Gaussian elimination, right, and solve systems of linear equations, right? Gaussian elimination in the best form is bounded by a quadratic time, etc., right? While your straightforward algorithm for two-colorability is, of course, linear. So generally, we are losing something. In general, we are losing something. The idea, well, the hope is that we might be able to do something in a more general way, for instance, right? So, well, that we don't know how to do before. And also say, like with SOS especially, what we're actually getting, and which many people like, that we are getting a uniform algorithm for all problems like that. Forget about this, I don't know, algorithm for two-colorability. Gaussian elimination rules, right? You don't need anything else. If you know Gaussian elimination, forget about everything else, in some sense. That was very useful with SOS, for instance. There has been this line of research that basically tries to show that, well, this SDP algorithms is basically can solve everything that can be solved. Right. That's I believe a very fruitful and useful direction. So from the terms of algorithms you would use in practice, no, I don't think so. I don't think so.
Okay, thank you. I see. Thank you very much. Any other questions?
I have another question about the proof in the end with the reduction. I didn't quite get it. Is it an example of how general technique work, or is it
basically,
just?
Yes, right. So that's more or less what that's the trick we invented, let's say, with all this interpolation mappings between, say, some domains, interpolation with things, and so on and so forth. So that's one of the tricks we invented. And this is basically how this stuff for polymorphisms work and so on.
So the same thing can be done with the different semi-lattices and.
Yeah, well, yes, you can do similar things in very general situations that are essentially the same. You encode something, you interpolate this encoding and decoding. You convert the CSP instance, you substitute stuff in the input polynomial, and you prove that the membership in the ideal is preserved under that. That is a general technique.
Okay, great, thanks.
Any other questions? Well, I think there are no more questions. Once again, thank you very much for a very nice talk. Everything was very clear. Thank you.
Okay,
Thanks everyone for joining. Goodbye.
See you later, bye.